Morning. One question. Yeah.
So I was confused because it's saying like so h prime of x is equal to f of x. So
Yeah.
this is basically a
H prime.
h prime graph.
Right.
So how would wouldn't we just read it like a normal graph where like it's increasing from like -7 to
No, remember this is the H prime graph. So this is a derivative graph. We have to treat it like a derivative graph. So anything above the x-axis is representing positive slope for the x graph.
okay.
Anything below the x-axis is going to be negative slope, right? The y-axis represents slope values. So this will be like slope 1, slope, slope 0, slope 3.
All right. And then on the test, are we gonna have like any h double prime graphs?
No,
or
no,
like
no.
anything
It'll
like
be
that?
H prime. Yeah. Same
Okay,
thing. Same thing on the AP
yeah,
exam.
because I was kind of worried about that because we didn't do any of that.
Right. Yeah.
Right.
But sometimes on the multiple choice, they would give you an F double prime graph. If they give you F double prime graph, just have to remind yourself anything above the x-axis is concave up, below is concave down, and all you can get from a F double prime graph is points of inflections, concave up and concave down intervals. Yeah. Okay, so worksheet 6. Okay, so we have the H prime graph given because this is f of x, but there's indication that this is H prime is f of x. And we have a starting point given to us. We have h of 0 equals 5. So that will be our anchor point. So part A says find h prime of h of -4. And h of -4 is going to have to involve the displacements as well as our starting point. So we're going to involve the formula, the rearranging of first theorem, which says any point I'm looking for is always going to be my initial point, or initial is always the given point, plus however much progress I've made from that point under the graph. So to adapt this formula, I'm going to say, okay, if I want to find h of -4, I'm going to start at h of 0 because that's what's given to me. Plus, and I want to be able to start at 0 and go to -4. So 0 to -4. Now, this is out of order initially, but I'm following whatever this formula says, which is whatever my my starting point is, that's where I need to start, and I need to end up at where I'm trying to reach. So now once I have this written down, I realize I would prefer to read the graph from left to right, and I'm going to allow the bounds to swap. But if I'm swapping the bounds, I have to make sure I adjust the sign change. So now the integral from -4 to 0, we're talking about this region here. And this is these are all geometric shapes here. I'm going to think of it as, okay, I see, oops, sorry, I see a triangle, I see another triangle here, I see a rectangle, and I see a smaller triangle here.
Wouldn't it be -4 to 0? You did -4 to 1.
-4 to, oh, sorry, yeah, you're right, yeah. I don't need the space, you're right. So it'll be 8 here. 1/2 base times height is 2. And then here, that's an area of 6, 1/2 base times height. So 6 plus 8 plus 2, 16. So h of 0 is 5. That's given to me, minus 6 plus 8 plus 2. Next up, h prime of 0. This is the h prime graph. So h prime of 0 is simply asking for the y value of the f graph. We're just going along with the definition here. So h prime of 0 equals f of 0, and f of 0 is that y value. That y value is 4. And h double prime of 1.5. We know h double prime must then be f prime. And f prime is asking for the slope of f graph. So I identify 1.5. 1.5 is somewhere here. And then this is just all part of this line here. This line all share the same slope. I just need to pick 2 points for me to do rise over run. So I pick this from this point to this point, down 4 over 1. Slope is -4. Questions so far? Okay, on what interval between -4 and 6 is the graph of h both increasing and concave up? So this is the h prime graph. Both increasing and concave up. So we can kind of remind ourselves what we're looking at. We're looking at the derivative graph here. So anything above the x-axis represents where h of x is increasing. Anything below the x-axis is where my h of x graph is experiencing negative slope. Anything on the x-axis is slope 0. So my only critical point that I have, only place where there's a slope 0 on the h of x graph is at x equals 1. So clearly between -4 and 1, my h prime graph is sitting above the x-axis. So that's going to represent positive slope. So my graph of h is rising in that interval from 1 to 6, below the x-axis, so negative slope. Next up, let's create our h double prime sign line. If we're looking at the h prime graph, then peaks and valleys, the max and mins of my h prime graph will represent points of inflections of the original graph. So the maximum steepness that the graph is going to experience, or the minimum steepness, relative minimum steepness, is going to be at -2 and at 2. And then to determine concave up, concave down, we just look at the slope of the F prime graph. Sorry, H prime graph. So positive slope on the H prime graph means concave up. Negative slope on the H prime graph means concave down. And then positive slope on the H prime graph indicates concave up. So increasing and concave down at the same time. So I put the sign lines directly above each other so I can see when both are going to occur at the same time. And it's going to be in this interval here from -2 to 1. Okay, part C. Let J of x equal to f of g of x. Find the tangent line equation to J of x at x equals 1. So we need to find order pair and find slope. So order pair first, J of 1 equals f of g of, if I plug 1 in for x, 2 times 1 is 2. So composite function here, I can find g of 2 first using my table of values. So g of 2 is 5. So f of 5 is what remains. F of 5, go to my f graph here. F of 5 is -1. Okay, there's my y value. Next up, we need to find the slope. Slope comes from the derivative, but for the composite function here, we got to go through chain rule to find the derivative. So there's an outside, inside portion here. Outside portion is my f bracket. The inside portion is my g of 2x. So we take turns with each derivative. J prime of x equals f becomes f prime. Keep everything inside the same. Times g of 2x becomes g prime of 2x. There's another chain rule hidden in here because there is also this inside portion as well. So that's going to be times 2. So it's like a nested chain rule here. You got that outermost portion, you got the inside, and you have the innermost portion, which is 2x, and each will have its own time and space for their derivative. Okay, replace every x with 1. G of 2 is 5, and then we're left with f prime of 5 times g prime of 2 times 2. And then we're just pulling those values from our table or our graph. So f prime of 5 using our table of values is going to be 1. G prime of 2, sorry, f prime of 5 using the graph. F prime of 5 is asking for the slope of the f graph at 5. The slope of the f graph at 5, rise over run. slope is 1. G prime of 2 is asking for slope of the G graph at 2, and G prime of 2 is -2. Multiply all that out, we get J prime of 1 cleans up to be -4. Here's our slope. We have our order pair, 1, -1, and then point slope form. Any questions, first page?
Did you just use any point and use it to 0 because it doesn't, oh, it's a.
Yes, yeah. So if unless there's a definition like this, if there was a definition that says the integral of f of x dx equals h of x from, let's say, 2 to x, then if it's this, then you just use that formula. Either I'll give you a formula or I'll give you a starting point for you to build off of so you're either using this definition or you're using the order pair and plugging it into the final equals initial plus displacement. Yeah, but if I don't give you this, I got to give you a starting point to work off of.
Just put like -4 straight in.
Exactly. So plug it in straight in, and whatever that gives you, that's your answer. There's no starting point. It is just built off of that. Yeah. Right. Yeah. So it's either one of these two. Mm-hmm. Okay. Good first page. Okay, second page. Part D, is there a time such that G double prime is equal to -1? Well, the issue, I mean, it'd be nice if G double prime was given to us, then you just look to see, okay, is there a value above -1 and below -1? And if there is, then I can just say IBT can get me to that point. But here, I don't have anything at the G double prime level, but what we do have is we have G prime, and we know G double prime is the slope or the derivative of G prime. So if I can somehow show that the slope of G prime is equal to -1, then I know that there must be a place where G double prime is equal to -1. And then that connection is applying mean value theorem. So we set up mean value theorem. Our G prime is continuous. We know that is true. It's given to us at the top of the page. We know it's also differentiable. And normally, my mean value theorem is f of b minus f of a or b minus a equals f prime. But I can take that mean value theorem and I can slide down to different derivatives, right? We can adapt it for any derivative. So if I do G prime of b minus G prime of a or b minus a, I can set that equal to G double prime of c. So if I can somehow show that the slope at the G prime level is equal to -1, then I can use mean value theorem to guarantee that there must be, if there's a slope of -1 between the two endpoints, there must be a slope somewhere along that curve that's also -1. So we use our endpoints that's provided for us, plug them in to our formula, and then use our table of values to grab those y values. So G prime of 5 using the table is 2. G prime of 3 using the table is 4. So change in G prime over the change in X is -2/2, which is -1. And because there's a slope between the two endpoints of -1 and the graph is smooth and continuous, there must be a -1 slope somewhere along that curve.
Brackets or parentheses at the end of your explanation right there.
This one, yeah, this one needs to be parentheses. For mean value theorem, it's bracket with continuity, parentheses with differentiability, but then the C value cannot land at the endpoint. It needs to land between the endpoints. Not for what I'm going to give you. But sometimes on multiple choice questions, sometimes they can be tricky. And, it could be like maybe part of a graph and they actually do mean value theorem and realize, wait, it's not differentiable. And so therefore it breaks down. So I won't give that to you. And typically on FRQs, they're trying to see if students understand the process of mean value theorem. So that's not going to happen. But I've seen on multiple choice questions where sometimes mean value theorem breaks down because it's not differentiable. So, but yeah, be aware of that. That's possible, but not on the FRQ. No, probably not. No, there's no IVT, but IVT does show up on FRQs. Yeah. So, and we saw yesterday, right? Sometimes they pair IVT and mean value theorem next to each other to see if students can distinguish between them. But I'm going to give you like mean value theorem rules.
Is the test gonna be like one full FRQ, like this front and back?
Right, just front and back.
Okay.
So this is a good one to review, but hopefully you guys also had a chance to look through page 11, 12, and 22 through 24. Okay, part E, we see a limit problem. So anytime we see a limit problem, we always do direct substitution. I mean, a lot of times it ends up being L'Hopital's rule, but we can't assume that, right? We always want to confirm what's happening at 4. So we always want to plug in 4 because it's possible that we may get a real number. If we get a real number, then there's no need to do anything else. We can just stop and say that's our limit. We only do L'Hopital's rule if we're getting 0 over 0 or infinity over infinity. But typically for these problems, it's going to be 0 over 0 that moves us into L'Hopital's. Okay, so direct substitution here, plug 4 in for x. We get g of 8. 4 in for x, we get 2 times 4 is 8. So g of 8 is -2 because that's what the table tells us. So e of -2 minus e of -2, that's going to be 0. And the denominator is 4 minus 4. So we get 0 over 0. We do get indeterminate form, which is allows us to move into L'Hopital's rule. So take the derivative of the numerator, take the derivative of the denominator, create a different version of the expression, and then we reevaluate the limit to see if that will get us down to a real number. So the rule for e to the u is e to the u times u prime. So we have e to the g of 2x times the exponent's derivative, and the exponent's derivative is g prime of 2x times 2. So there's quite a bit going on just to get that derivative of e to the g of 2x. Any questions here? Okay, so next up, e to the -2 is a constant, so the derivative of that is 0. X derivative using power rule is 1. 4 goes to 0. And now let's reevaluate and see if that will help us get to something other than the 0 over 0. So plug in 4 in for x. We get g of 8, again, is -2. G prime of 8 is 5 times 2. So we get 10 e to -2 or 10 over e squared. I do want you to know how to expand logs. Yeah.
Expand.
So like, if it was like, natural log of g of x, f of x. And to find the derivative, before you find the derivative, I want you to expand it out. So natural log of a times b will be natural log of a plus natural log of b. And then from there, you can find the derivative, right? U prime over u, u prime over u. Yeah. So yeah, if you see a messy log expression, always expand it out first before you find the derivative. Okay, find the maximum value. Maximum and minimum value is indicating for us to apply extreme value theorem. And extreme value theorem means we want to pull endpoints and critical points from the slope sign line. And our slope sign line, we had it on the previous page, which was -4, 1, and 6. So we're going to test -4, we'll test 1, and we'll test 6. All into our final equals initial plus displacement formula. We already have h of -4 from the previous page, so we can carry that over to -11. Next up, I want to find h of 1, and I also want to find h of 6. So h of 0 plus the displacement from 0 to 1. The area, the triangle area from 0 to 1 is 2. And then the area involved from 0 to 6 is the triangle plus the another triangle, but it's below the x-axis, so we do 2 minus 10. Oh, or I can call this h prime. Yeah, I should use f of x because they say f is h prime, and I'm just referring to this f. But yeah, you can say h prime. Oh, you mean for this?
Yeah.
Yeah, it's always going to have to be h prime. It's always going to have to be the area under the derivative graph is what's going to give us the displacement.
Okay.
Yeah. Okay, so once we have our candidates, we compare our y values. The highest y value is 7, so that's our estimate.
Can we use h of -4 as a
As your starting point? Yeah, you can do that.
And you don't have to say anything like it's continuous or anything.
Right, yeah. On the AP exam, they are happy with just students showing testing the valid points and then just stating out how they got there, how their conclusion comes down. And part G looks like a messy problem, but it's messy in the sense that that's an indication for us to go through, use substitution. We don't have a rule that can handle this starting point. So we let our u value be what's inside that radical. If you want, you can rewrite that radical as bracket to the 1/3 to help you see, okay, I want what's inside that radical. My u value is g prime of 1/3 x. I know I have to find a way to get this to pair up and cancel out. So I need to move to the derivative du over dx. G prime because becomes g double prime. There's a little bit of chain rule there times the derivative of the inside portion. So 1/3 x times 1 becomes 1/3. Cross multiply, solve for dx. We get 3 du over g double prime of 1/3 x. We make our substitution, replace the bracket with u, replace, or g double prime stays initially. Dx gets replaced with 3 du over g double prime. Clearly see there's a canceling out here. There's a leftover 3 that we have to pull in front. And now, after use substitution, we should be looking at a much easier problem for us to move into our calculus step. So we go through power rule, add 1 to the exponent divided by that exponent. Clean that up, replace the u back in terms of x, and then we can plug in our upper and lower bounds. Once you plug in your upper and lower bounds, replace the g prime in terms of a numeric value. But once you're down to a numeric value, you can just leave that alone. That is sufficient.
So you just like make all the points of X like on your bound U and then.
Sure, yeah, you can do that as well. You can leave the 15/6 u to the 6/5, leave it in this form. Plug the 6 and 9 into G prime of 1/3, get that associated U value, and then use those U values to plug in. I think it'll end up being 4 and 2, and it'll get you from here, yeah. Or 4 and -2, get you from here.
5/2.
It's 3 divided by 6/5,
Okay.
which ends up being 15/6, which I reduced that to be 5/2. I can leave it as 15/6. Yeah, if you leave it at 15/6 at the end, that's fine. You don't have to reduce down to 5/2. So spend some time looking over this sheet, looking over worksheet 5. Look over page 11, page 12, 22 to 24. Let me know if you have any questions from any of those problems.
Any questions in the test?
It's like this length. I'll say maybe 7 or 8 parts. Whatever I can fit onto 2 pages is what you're gonna see. Yeah, I think we covered pretty much everything. Yesterday, we saw some average value theorem. We also saw a little bit of application of second theorem.
Stuff from yesterday gonna be on.
Yeah, I mean, we definitely want to make sure. I mean, they're essentially the same thing, right? Worksheet 4 on page 20. Well, the key is on page 25, but page 22 to 24.
Stuff like for the.
Like rated, rate out. Yeah, that's next week.
Okay.
Yeah, the rating, rate out, Riemann sum, solving differential equations. That'll be next week.
Did we solve any problems that had like a integral instead of like a point on the graph? For like this, instead of having a point, we had like an integral like you showed us.
Oh, yeah, yeah. Yeah, page 11 has that. I'll pull the key up. So this is page 14, which has the key. It says, find the absolute minimum, absolute max value from 0 to 6. We know that if this is the derivative graph, we're gonna have to test 1.5, 4, 0, and 6. And this is the definition here. So we're just plugging those values directly into h of x and then deciding which of those values has the highest and lowest y values.
Oh, okay.
Yes, yeah. So, if I give you derivative, any derivative, it'll just be the ones that we know, either that are, that are very familiar, right? Either e, natural log, sine, or cosine. See that? I expect you guys to be the final derivative of sine and involving sine, cosine, and exponential function e.
Will there be anything like K on page 24 where you have to use central theorem?
Yeah. We need to know how to do that. Yeah, if I'm asked to find the derivative of a function that has an integral in it, then I have to use second theorem. So second theorem says if I'm pairing a derivative on top of an integral, I'm going to plug my upper bound in for the variable times the upper bound's derivative. We're just going through page 11, 12, 20 through 24, seeing if you have any questions.
You print something out. Thank you.
Okay, see you in class. Do you have any questions?
Sorry, I was at an NHS meeting, but for this small review that we have,
Yeah.
I was just wondering how you chose. So for this right here,
Okay, so
when you're doing I guess I was just having trouble connecting h of x to the f graph. So
Right,
could-
because f is the h prime.
Okay.
So here indicated that h prime, this is the h prime graph,
Okay,
because h prime is equal to f of x.
so then when this is the h prime graph, and you're doing your slope sine line.
You look at above and below the x-axis as positive and negative slope.
Okay, so
On the x-axis is your slope 0.
okay, and so then if this was the h graph, you would look for your max and mins for your.
You're not gonna see that. If you're gonna get a derivative graph of some sort.
Okay,
Yeah.
okay.
And the peaks and valleys will be your points of inflections.
Okay.
Yeah, yeah.
For like formulas, we got like just triangle, rectangle, like.
Semicircle, yeah. Yeah, that's it, yeah. I would say trapezoids, but I think it's easier to just split a trapezoid up into triangles and rectangles. Okay, see pass.
For something like K,
Yeah.
we didn't use second theorem, right?
We use second theorem, right? So anytime your function is defined with the inner coordinates
Mhm.
and variables, if you're asked to find the derivative of something in this form, you have to go through second theorem
Okay,
in order to keep track of what's left over.
what page number is this one?
This was page 27 is the key. I think the blank page is a little bit earlier.
Okay,
Do we need to know first theorem?
Yeah, you guys have been applying first theorem. It's just. You guys have been using first theorem. For like all the use substitution problems, it's just first theorem.
What's F of C?
Oh, A, sorry, A.
Okay. When you're doing average value, why would it be like F of C or F prime of C is equal to the average value? Why would you use C?
It's just to indicate a different variable than the X that you see here. Typically, that's the notation that we're looking for. The X value solution is represented as C. I think we use that C again in mean value theorem and Rolle's theorem as well.
What's Rolle's theorem again?
Rolle's theorem is the same thing as mean value theorem. Mean value theorem is this. But the slope at this level can be anything. It could be, slope of 1/3, it could be slope of 2, it could be slope of 3. So we're just finding whatever slope we find between the endpoints and then guaranteeing that slope somewhere along that curve. But Rolle's theorem is looking specifically for slope 0. So because it's looking for slope 0, we have more restrictions. We need these to be the same values in order for the points to be directly across from each other. We need that slope 0 between the two endpoints so that we can guarantee a slope 0 somewhere along the path.
So it's the same formula, you're just looking for slope 0.
Exactly,
Okay.
yeah. So, right, exactly. And because you're looking for slope 0, we need the endpoints to be the same y value.
Okay.
But mean value theorem, it can be the same, but it also can be different.
On the test, we could use either.
Yeah, you can, if it's Rolle's theorem, you can say mean value theorem and be okay. But if they refer to something as Rolle's theorem, they need to recognize, okay, it's mean value theorem, but it's looking for slope 0 between the two endpoints. But essentially, the reasoning between mean value theorem and Rolle's theorem is the same conditions, same formula.
You said like a certain part of our is coming from our homework.
Right. So I think it's gonna be like 50 points from your homework, 50 points if you put it down to the vertical. So you have a built-in curve for your grade that.
Thank you, Steve. All right, bye.
Bye, thank you.